Arvind has done exceptional work to more or less complete his PhD thesis. I'm assuming complete. Uh, Through the last couple of years of pandemic, life was very difficult for students. Uh, I actually did not come to the campus till recently. So all my interaction with Arvind and other students was remote. But through his excellent leadership, collaborative qualities, which resulted in lots of work with Eric Pop's group and Philip Wong's group, through his own vision, he has done fantastic work in his PhD dissertation, as you will see in the next 1 hour or so. So Arvind, take up the podium.
Okay, thanks for the kind introduction, Professor. Let me share the screen. Can you see the slides?
Yep.
Okay. Hi, everyone. Thanks for coming. I am Aravindh Kumar. I'm advised by Professor Krishna Saraswat and Eric Pop. And I'm going to talk about improving contacts and doping to two-dimensional transition metal dichalcogenides, or TMDs. My research is focused on transistors and how to make them faster. And so what are transistors? All our personal computing devices like laptops and smartphones today have a CPU in them. And the inside of a CPU looks like this die shot. And a state-of-the-art CPU today has about 1 billion small devices called transistors. And they look like this. Today, the transistor has dimensions in tens of nanometers. So what is the function of a transistor? It is a 3-terminal device with a drain, source, and a gate. And when a low voltage is applied on the gate, the conduction between the source and the drain is very low. And when a high voltage is applied, the conduction increases. So the transistor acts like an electronic switch. So if we connect the transistor to an LED and a battery as shown, and then apply a high voltage, the LED turns on and starts glowing. The Moore's law is an observation which states that the number of transistors on a microchip doubles every 2 years. And that has been the trend in the semiconductor industry for the past 5 decades, as shown in this plot on the left. The y-axis here is in log scale, so this growth is actually exponential. Looking at the plot on the right, the global semiconductor industry has grown its revenue from about $3 billion in the late 1970s to almost $500 billion in 2020. And this is more than 150 times increase. And for context, in the same time frame, the worldwide GDP increased by only 10x. This exponential increase in the transistor count and the industry revenue has been mainly driven by the geometric scaling of these transistors, mainly silicon transistors. Every 2 years, the area footprint per transistor reduces by half, but we are approaching the limit of geometric scaling in the planar direction. Now, the industry is transitioning to these gate-all-around nanosheet transistors, and these nanosheets are only 5 nanometers thick. The way forward to scale these nanosheets further is to make them thinner and thinner. However, silicon performance degrades if you make them too thin. And that's where these novel materials called transition metal dichalcogenides, or TMDs, come in. So TMDs are a class of layered materials made of units of 1 transition metal cation atom and 2 group 6 anion atoms. MOS2 is the most widely studied TMD and will be the primary focus of this talk. As shown in this crystal structure on the bottom left, it has a layered structure with no dangling bonds. And we call these ultra-thin layered TMDs as 2-dimensional or 2D TMDs. The calculated electronic band structure of a monolayer MOS2 is shown on the right, and it has an electronic band gap of 2.3 eV, which is very good for transistor applications. And further, the band gap can be tuned by changing the layer number of the MOS2. For example, in its bulk form, MOS2 has a band gap of 1.2 eV. So why should we study these TMDs? As mentioned before, TMDs are really promising for nanoscale transistor applications. In the state-of-the-art transistors, the physical gate length is still stuck at 20 nanometers. And in order to scale the gate length below 10 nanometers, channel thickness less than 2 nanometers is required. And this becomes problematic for conventional semiconductors like silicon and germanium because the mobility degrades at these very thin limits. Whereas TMDs, on the other hand, they retain excellent mobility even at the monolayer limit. And this is because of their inherently layered nature. The other promising application area is monolithic 3D integration. And here, it is proposed that we can stack layers of compute and memory on top of each other to continue the life of Moore's law, but we would also get performance and efficiency benefits by reducing the interconnect power dissipation and delay. TMDs are promising here because we can deposit them on the second layer and so on at a low temperature, which would not affect the metal lines in the previous layer. And further, lattice matching is not required for TMD growth, so high quality growth is possible on multiple substrates. Silicon deposition on the second layer is problematic because it requires high temperatures and would melt the metal lines in the previous layer. So the conventional silicon transistor shown on the left is gated from the top, but in this talk, we would be focusing mainly on these 2D transistors, which are gated from the bottom through the silicon substrate. And we do this to simplify the test structure and to study one problem at a time. This part in the middle is called the channel, and this 2D channel here is just representative. It's not to scale. The interface between the metal contact and the 2D channel has this associated resistance called the contact resistance. And this has been the major problem preventing the adoption of TMDs. And the contacts are a problem because as we scale down these devices geometrically, the other components like channel resistance scale accordingly, but the contact resistance increases. And that's why even in silicon technology, the relative contribution of contact resistance as a proportion of the total resistance increases with each technology node. In MOS2, this problem is hard to solve because all the metal work functions spin very close to the conduction band edge of MOS2, but still cause this significant Schottky barrier height. And that leads to this, the barrier, Schottky barrier height, which has to be overcome by an electron in order to enter the channel. And this is the reason behind the high contact resistance. And one explanation for the spinning effect is the presence of sulfur vacancies in the MOS2 film. So I talked about contact resistance in the previous slides. Here I want to talk about contact resistivity that is commonly reported in silicon and other conventional semiconductors. Looking at this test structure on the left, where the current direction is perpendicular to the contact interface, this contact resistivity is nothing but the contact resistance, which is the interface resistance normalized by the contact area. But in an actual transistor, the current conduction is in 3D and there's a lot of current crowding going on. So most of the current enters the contact in this characteristic length called transfer length, which is different from the actual contact length. In silicon and other conventional semiconductors, the transfer length is in the range of 1 micron. So it becomes important to study both the ρc and the LT as we are dealing with contacts which are in the range of 1 micron or shorter. But in TMDs, especially monolayer TMDs, the transfer length has been estimated to be less than 5 nanometers, which means that most of the current enters the contact at the inner edge. And this is because of depletion of electrons under the contact and due to the very ultra-thin nature of these TMDs. So for the rest of this talk, I will be talking about contact resistance, which has units of ohm micrometer or ohm micron. When I started working on this problem, there was a significant gap between the best reported contacts and the industry requirements given by IRDS or International Roadmap for Devices and Systems. But we are still far away from the quantum limit, and which meant we had plenty of room to improve. So in the next 2 sections, I will describe our efforts to bridge this gap. First, I will talk about how we set up a platform for reproducible and rigorous analysis of contacts to monolayer MOS2. Then I will talk about how we use this platform to develop really good alloy contacts to monolayer MOS2. And in the final section, I will talk about our work on understanding the doping effect of aluminum oxide on this TMD called WS2. So let's look at the robust contact analysis platform. This transfer link method structure, or TLM, is the most widely studied structure or most widely used structure for studying contacts in these materials. And it's nothing but a series of transistors with different channel lengths. And since the total transistor resistance follows this equation, where this is the sheet resistance and the contact resistance, we can, by testing each of the transistors, we can get a plot like this and obtain the contact resistance from the y-intercept and the sheet resistance from the slope. And from that, we can extract the effective mobility. When I started my PhD, the contact analysis in 2D semiconductors had a lot of room to improve. Many contact studies did not report error bars or reported unphysically large error bars. The figure on the right shows a famous paper in Nature Materials, which claimed record low contact resistance. And however, they did not publish their extracted errors, which is way too large to make any meaningful physical conclusion. And this is because the Y values of these data points are in hundreds of kilo micron, whereas the intercept is less than 1 kilo micron. So this leads to large uncertainties. Also, many studies reported only hero devices or one-off devices with good performance. So we wanted to make a few improvements in the analysis of contact resistance, including rigorous error extraction and testing of hundreds of devices to get the RC distribution, in addition to reporting just the best devices. And we are able to make hundreds of MOS2 transistors because we can grow monolayer MOS2 by chemical vapor deposition using this 2-inch diameter tube furnace. We use solid sulfur and solid moly oxide precursors. The MOS2 chip after growth is shown here. And this is how the MOS2 monolayer looks like in the center of the chip. So we can get uniform monolayer MOS2 over a 1 centimeter squared area. Let me describe our TLM structures in more detail. For the study, we made 72 TLM structures as shown in this mask layout. Then each TLM structure is made of 6 transistors with channel lengths ranging from 100 nanometers to a micron. So we have a total of 432 transistors. And this is the electron microscope image of the TLM structure. The black strip is the MOS2 channel, and the vertical lines are the contact electrodes. So we test each of these transistors and perform threshold voltage extraction and adjustment to account for the VT variation. Then we do linear regression on the total resistance as a function of channel length to get this plot. And from here, we extract the contact resistance and mobility. And this is a schematic of a typical backgated MOS2 transistor. So how do we make these TLMs? First, we take heavily doped P-type silicon wafers and grow dry silicon oxide on top. Next, we grow MOS2 at 750 Celsius by chemical vapor deposition. And then we pattern these regions and etch away the MOS2. And then we deposit contact pads. And next, we etch the part in the middle to form a rectangular channel. And then we deposit the metal contacts on top of MOS2, as shown here. Then we test these devices without any capping. And after that, we carry out encapsulation using atomic layer deposition and remeasure the devices. We use 50 nanometer silicon oxide backgate dielectric here because any thinner oxide would be damaged by the MOS2 growth, which happens at a higher temperature. So we are showing the IDVG characteristics from all the 432 transistors grouped by the channel lengths. Again, the channel lengths range from 100 nanometers to a micron. And the blue curves are measured before capping and the red curves after capping. So from the shift in the curves, we can see that the capping induces some doping. And that's confirmed by plotting the VT distribution, which shows that the the threshold voltage shifts to the negative as after the capping occurs. So from those IDVG curves, we extract the contact resistance and mobility and show their distributions here as CDF plots. As a quick primer, the CDF at, let's say, 2.5 kilo micron is just the proportion of devices with their contact resistance less than 2.5 kilo micron. So we are showing the distribution of the contact resistance here. And each data point on this curve corresponds to a single TLM site, and the horizontal error bar corresponds to the standard error of the linear fitting. So we see that capping improves the not only the mean contact resistance, but also the variation. And the effective mobility is plotted on the right. The mobility improves as well. And the reason for this is that the capping process protects the channel during the testing, as well as it removes the adsorbates on the channel like moisture and oxygen molecules during the capping process. So why does the contact resistance improve with capping? Even if aluminum oxide dopes, we compare the RC at the same channel carrier density. So what's going on? One explanation is that the Schottky barrier height changes due to the aluminum oxide capping. And to understand this, let's look at the band diagram of a Schottky barrier. The conduction to the Schottky barrier depends on the Schottky barrier height. So a reduction in this would increase the electron injection. But there's another explanation. Going back to this schematic, the total transistor resistance is made of the contact resistance as well as the channel resistance. So this acts like a voltage divider network. So an improvement in the mobility because of the channel passivation would lead to a reduction in the RCH, and more voltage falls across the barrier and the barrier gets more activated. So a reduction in the RC occurs. So to test this hypothesis, we did TCAD simulations of this MOS to transistor. And for a fixed Schottky barrier height of 0.25 EV, the contact resistance does go down as a function of mobility for 100 nanometer channels. So the takeaway from here is that when comparing two different contacts, we must ensure that the compared devices show similar mobility. Now let's look at the statistical regression of TLM data. In the previous slides, we looked at each TLM independently and plotted the distribution of the RC and mobility estimates. But the other way to look at it is to collect all the data and do a single regression. And this gives us a contact resistance of 2.6 kilo micron, which is more of an averaged and conservative estimate. So one observation here is that looking closely at the shorter channels, there's a clear deviation from linearity at the 100 nanometer channel. And we're doing all this analysis for a low VDS of 0.01 volt. So we redid the same analysis for a higher VDS, and we see that the nonlinearity is much weaker in this case. So this hints at the nonlinearity happening due to some Schottky barrier or electrostatic effect that changes with the VDS. So we study the electrostatics in these backgated transistor structures to understand why the nonlinearity occurs. In the TLM analysis, we assume that the backgate behaves like a parallel plate capacitor to induce electron density in the channel. But does that hold true at short channels? Before we begin the analysis, we first define scale length, which determines the electrostatic limits in a transistor. In the long channel case, which is defined as the transistor channel length being much longer than the scale length, the electric field lines look very perpendicular to the channel for the most part, except for some electric field fringing near the contact edges. These fringing fields form a very small part of the flux. So this situation is very analogous to the parallel plate capacitor. But in the short channel case, where the channel length is close to the scale length or even lower, these fringing fields form a greater part of the flux. And so the parallel plate capacitor model might not be entirely accurate here. So here I want to note that even though MOS2 has excellent intrinsic electrostatics, we are using a thick backgate oxide, which would limit the scale length. So we did electrostatic simulations of this transistor structure in COMSOL to determine the scale length. And this plot shows the heat map or the color map of the electrostatic potential and the electric field lines. And we can see that there's a lot of fringing of electric field lines close to the contact electrodes. So here we plot the scale length as a function of the backgate oxide thickness without and with capping. And for this 50 nanometer backgated silicon oxide backgated device with the encapsulation, we see that the scale length is 200 nanometers. And that is quite large because the shortest channels that we have is 100 nanometers. So this is shorter than our the scale length. So the parallel plate capacitor model is not entirely accurate. But how does this affect the actual electron density in these transistors? So we did TCAD simulation of this structure, and we are plotting the electron density for two different channels, a long channel 1 micron case and a short channel 100 nanometer case. And we see that the electron density or the electron depletion is greater in the shorter channel and extends into the channel further. So we extract the RC or the contact resistance for these structures, and we see that there is an increase when you reduce the channel length. So this can be explained by the greater depletion in the shorter channels, causing the Schottky barrier to be wider and hence less injection at the contacts. So one solution for this problem is to reduce the backgate oxide thickness because that would reduce the scale length and improve the electrostatics. But in the second section, we would see that this problem actually disappears when dealing with good contacts that have a small Schottky barrier height. So summarizing this section, we set up a platform for automated chip scale testing of MOS2 devices. This was achieved using a semi-automated probe station and an encapsulation process using ALD aluminum oxide. The capping improved both the RC and mobility, but caused slight N-type doping. TCAD simulations showed that the measured RC depends on the mobility as well. So careful mobility comparison is also required when optimizing the contacts. We identify the deviation from linearity at short channels from the TLM data, and we attribute this to the large scale length of 200 nanometers in these transistor structures. And further simulations showed that this large scale length causes greater electron depletion in the shorter channels and hence a nonlinearity in the TLM plots. Now, I will talk about how we use that contact analysis platform to demonstrate sub 200 ohm micron alloyed contacts to monolayer MOS2. So going back to the slide on contact resistance, MOS2 has bad contacts because of Fermi level pinning, which is caused by sulfur vacancies. And the metal deposition process itself induces some sulfur vacancies on the MOS2 surface. So what if we could develop a low damage metallization process? This could reduce the interface defect density and weaken the Fermi pinning effect. So as a first step, we study the effect of different metals on MOS2. So previous work from Stanford showed that high melting point metals like gold cause a lot of damage on MOS2 when deposited on top of MOS2. So we wanted to see how the low melting point metals like indium and tin, how they would affect MOS2. And to do that, we did Raman spectroscopy using this test structure where the MOS2 is capped with 2 nanometer of the metal. So the Raman spectra is shown on the left, and this peak on the left is called the E prime peak. And the width of this peak correlates to the MOS2 defect density. As you can see, the indium and the tin capped MOS2 show E prime peaks, which are almost unchanged when compared to the bare MOS2, whereas the gold MOS2 has a much wider peak. So we take these peak widths and plot them versus the metal melting point for various different metals. And we see that there's a clear correlation between the peak width and the melting point. So low melting point metals like indium and tin they minimize the damage during deposition on MOS2. So we decided to make contacts with indium and tin to see how they would perform. And for this study, we used three different contact schemes. So we made 40 TLMs for each scheme and 6 channel lengths per TLM. So that's a total of 240 transistors per contact scheme and 720 in total. We used the gold contacts from the previous section as the control device, and we tested these new indium and tin contacts, which are made by depositing 10 nanometers of indium or tin, followed by 25 nanometers of gold. So we tested these devices after the aluminum oxide encapsulation, and the TLM fits are shown on the right. So pure gold gives us an RC of 2.1 kilo micron. Tin gold shows 1.3 kilo micron, and indium gold shows 0.4 kilo micron. So tin gold is 1.5x and indium gold is 5x better than pure gold contacts. This analysis masks the variations across the chip because the MOS2 film as grown has a lot of spatial variations coming from the material quality. So again, we look at each TLM individually and plot the distributions as CDF for RC, mobility, and the drain current. And one observation is the indium gold contact does the best in terms of RC, so it gives us the best contacts. But in terms of variability, the tin gold contacts have the least variability. But the variability is strongly correlated between the RC and the mobility, which indicates that the MOS2 growth itself is the main source of variation. So we take a look at this best TLM, and that had indium gold contacts. So the IDVG dual sweep curves shown on the left shows really very minimal hysteresis. And the lowest contact resistance we obtained was about 190 ohm micron, which is among the lowest reported on monolayer MOS2. And the IDVDS on the right shows a high drain current of 360 microamp per micron at 1 volt VDS. And the nonlinearity here indicates that that's the conduction is limited by self-heating. So here we benchmark the best indium gold and tin gold TLMs with other good contacts reported in the literature. We are looking only at contacts to monolayer CVD MOS2. Our best indium gold contacts showed a contact resistance of 190 ohm micron, and the best tin gold contacts showed 270 ohm micron. Further, the dependence of these new contacts on the carrier density is much weaker when compared to the silver gold and the pure gold contacts, which are commonly used. So this indicates that these new contacts have a lower Schottky barrier height. So next, we did material characterization to study the chemical composition of these metal stacks. We first did depth profiled XPS on these metal stacks before any anneal. So we are looking at this structure where the MOS2 is capped with 10 nanometer of indium and 40 nanometer of gold. And the XPS shows that the gold and the indium signal is present throughout the metal stack. So there's a lot of intermixing going on. And similarly, in the tin gold stack, we see gold and tin present throughout. So yeah, intermixing happens here too. To see exactly what's happening at the interface of these indium gold contacts, we did these cross-section TEMs of the indium gold contacted MOS2 transistors. So we are looking at this transistor structure and zooming into the contact interface. We see that the MOS2 monolayer visible here is looks undamaged and continues without any breakage into the channel region. And EDS spectra show that the gold and the indium are present throughout the metal stack, again confirming that intermixing is going on. And the molybdenum signal here confirms the presence of the MOS2 channel. So to determine if just intermixing happens or if any alloying is occurring, we did X-ray diffraction measurements before and after anneals. And we studied these structures of 10 nanometer indium and 25 nanometer of gold on bare silicon. And we see here that there's no alloying before the anneals, but after the anneal, we see this distinctive alloy peak of Au3In, and the indium peak vanishes. And in the case of tin gold, partial alloying happens without any anneal, but the alloying is completed after the 250C anneal. And again, here the tin peak is gone. So in both cases, the low melting point metal is fully consumed. So the metal stack exists as a mixture of the alloy and the pure gold. To understand the properties of these identified alloys, we look at the phase diagrams of the indium gold and tin gold systems. And the Au3In here is expected to remain solid up to 482 Celsius. And in the case of tin, the alloy should be solid up to 521 Celsius. So these alloys should remain stable and solid at 450 Celsius, which makes them back end of the line compatible and manufacturable. So as a first step in testing the temperature tolerance, we look at the IDVG of 50, 100 nanometer channel devices for each of these contact schemes. And this was tested after the 250C ALD. So the general behavior and the on-off ratio of the IDVG curves are comparable to pure gold. So these new contacts are stable at 250C. To further test the temperature tolerance, we performed rapid thermal annealing of the indium gold contacted MOS2 transistors. And this was done at 350 Celsius in nitrogen ambient for 20 minutes. The dual sweep IDVG shown here shows negligible hysteresis, but there's a VT shift after the anneal, and that can be also seen in the increase in current in the IDVDS. And this VT shift could be due to the effect of the anneal on the Al2O3 capping layer. When looking at these metal lines in SEM, we saw no voids or any changes in the morphology of the metal electrode lines. So alloying does make these contacts stable at 350 Celsius, even though the indium melting point is just 150C. So back to this slide, this is how the landscape of contacts to monolayer MOS2 looked like in 2018. And today we have almost bridged the gap. And this is my work. And so we have come very close to the IRDS limit. This data point here uses bismuth gold contacts, which is incompatible with processing above 250 Celsius. So we have, from our work, we have made the best manufacturable contacts to monolayer MOS2 to date. So summarizing this section, we identified a correlation between the metal melting point and the MOS2 damage. So lower melting point metals like indium and tin induce the least damage among the metals. Then we presented a statistically rigorous comparison of these contacts by testing 30 TLMs each. And we see that indium gold improves on the pure gold contact by about 5x. And the TLM with the lowest RC had indium gold contacts and showed 190 ohm micron RC. And this is among the lowest shown on monolayer MOS2. XPS and XRD studies reveal that alloying occurs, and these alloys should remain stable at 450C, making them manufacturable. And we test that on indium gold using a 350C anneal, and these contacts do remain stable. In this final section, I will talk about our work on understanding the electron doping effect of aluminum oxide on TMDs. So why is doping important? In the previous section, we talked about reducing the contact resistance by engineering this Schottky barrier height. But we could also dope the channel by depositing this doping layer, and this increases the carrier density in the channel and modulates the width of the Schottky barrier, which increases the electron injection and hence would reduce the contact resistance. Doping would also become more important for adoption of top gate 2D transistors. Here, the gate overlap between the gate and the source or drain electrodes would help with gating these contact regions, but it leads to these large parasitic capacitances, which would slow down the transistor and make them power hungry. So rather, we would like to have these underlapped gates with the extension regions doped by these doping layers. So in the study, we look at the doping of another TMD called tungsten disulfide or WS2 using aluminum oxide doping layer. We chose WS2 here because it is theoretically predicted to have a higher electron mobility than MOS2. And more importantly, it is shown to be ambipolar, so it can conduct both electrons and holes efficiently. So that is good for CMOS logic. Here we study bilayer WS2 transistors that was obtained by mechanical exfoliation. And the process of depositing alumina is similar to the Al2O3 encapsulation we used earlier. So we first start with the backgated WS2 transistors, and then we deposit this aluminum seed layer by E-beam evaporation and expose it to air to let it oxidize. Then we deposit aluminum oxide by ALD. So this aluminum oxide doping has been demonstrated previously on MOS2 using 150C ALD. But in the work, they found that the initial on-off ratio was very low and needed a subsequent nitrogen anneal to fix it. So we think this is because of the presence of carbon and hydrogen interstitials in these low temperature ALD layers, which could cause degradation of the transistor characteristics. So we tested different temperatures and we chose a 200C ALD temperature for the doping study here. And experimentally, we see that it is quite effective at doping the channels, as seen from the shift in the IDVG. There's a lot of N-type doping going on. But importantly, the on-off ratio of 1E8 or 8 orders of magnitude is retained without any post-deposition anneals. And we also see really good off-current and high mobility of 30 centimeters squared per volt second. The IDVDS shows a max current of 160 microamp per micron, which at the time of the study was the highest reported on WS2. So we study the stability of this doping technique over 21 months. The IDVG right after the doping is shown here. And we remeasured these devices after 21 months. And we see that there's a lot of degradation in the subthreshold swing, the on-off ratio, as well as the hysteresis. And the reason for this is the formation of hydrogen impurities and hydrogen interstitials in the aluminum oxide layer because of exposure to moisture. And again, this creates these deep level traps, which could act as traps for the MOS2 channel. The good news is that nitrogen anneal is known to cause out diffusion of these hydrogen atoms, and a 40 minutes 200C anneal caused almost perfect recovery of the original electronic performance. So to further understand the atomistic origins of the doping and why it is happening here, we look at atomically constructing these structures and doing some DFT calculations to see what's going on. As a first step, we calculate the band structure of this monolayer WS2, and it shows a Fermi level slightly below mid-gap, so it's mildly p-type. Next, what we do is we take this monolayer WS2 and the aluminum oxide layer, put them together and relax them to get the lowest energy configuration. And then we can plot the potential profile through the interface, and this lets us align the undoped and the doped WS2 to get the Fermi level difference. And that's what we are showing here. We tested different configurations of the Al2O3 layer, different surface orientations, different surface terminations. And we see that in all these cases, there is a clear N-type doping that's going on, as seen in this Fermi level shift towards the conduction band edge. So here we plot the Fermi energy for each Al2O3 configuration, and we see that the aluminum terminated case is the most effective at the N-type doping. Then we studied the effect of oxygen vacancies in these layers by removing these oxygen atoms and redoing the calculations, and we see that the Fermi energy shifts towards the conduction band, but this effect is much weaker compared to the effect of different surface terminations. So in conclusion, the dipole effect of the aluminum surface termination along with the oxygen vacancies or partly the reasons for the doping effect. This supports the use of aluminum seed layer in our doping experiments since it increases the likelihood of the aluminum termination and creates an oxygen doping layer. So summarizing this section, we experimentally demonstrated N-type doping in bilayer WS2 by, so this doesn't degrade the on-off ratio and retains excellent mobility. We tested the devices again after 21 months and found that the performance degraded quite a bit, but this was reversed by a nitrogen anneal. We performed DFT calculations of the heterostructure, and it predicts N-type doping for oxygen deficient and aluminum terminated Al2O3. So here are my research contributions. I developed a processing platform for robust testing of metal contacts to 2D TMDs. This platform can be used for developing solutions to other research problems too, like doping and gate dielectric engineering for these 2D TMDs. Then we studied the effect of scaling on these backgated transistors and found that a large scale length of 200 nanometers, which is limited by the oxide thickness, is causing the non-idealities in the contact measurements. We demonstrated the best manufacturable contacts to monolayer MOS2 using indium and tin contacts. And this was done using testing of many devices so this was shown with statistical rigor. We also show that alloying can be used to make these contacts highly temperature tolerant. And finally, we experimentally demonstrated N-type doping in bilayer WS2 using these Al2O3 layers without degrading the on-off ratio or mobility. And we studied how stable these doping techniques are. And turns out we need a much thicker encapsulation layer to make them more stable. And DFT calculations showed that this doping is largely due to aluminum surface termination and oxygen vacancies in the Al2O3 layer. So here I would like to acknowledge my advisors first. Professor Saraswat has been very supportive of me throughout my PhD journey. I enjoyed a lot of freedom to pursue my research interests and set up collaborations with all researchers from any institute in the world. And during my PhD, my ideas and experiments failed very often. And this unflinching support really helped a lot because it gave me that comfort for trying out new ideas. And not only that, Professor Saraswat also gave me great advice outside research about general life. So honestly, I don't think I could have asked for a more caring and supportive PhD advisor. Thank you, Professor. And Professor Pop, thank you for adopting me as a student and giving me great research advice over the years. My research on 2D semiconductors would not have been possible without the expertise of Professor Pop and his students. I also learned a lot from Professor Pop on how to make good slides, good presentations, and write good papers, and paying a lot of attention to details. Yeah, thank you. So I would like to thank my other committee members. Professor Wang, EE316 was one of the most useful courses for my PhD research. And I also loved hearing your insight in the 2D meetings. Thank you. Professor Chowdhury and Professor Mannix, thank you for agreeing to be on this committee. Okay, now I want to thank my lab mates and colleagues here. First, I want to thank Alvin Tang. He has been a great mentor and friend throughout my PhD. And I got started with my research thanks to his excellent MOS2 growth. And he was really patient with my process issues because I was doing the processing for him. So his project gave me a test bed to hone my processing skills and really get started. And we had a great tag team going on, working day and night to solve those issues. Hope to work with you in the future. And my Saraswat group friends, especially Pranav, Kusha, and Raisul, have been very supportive of my PhD, my research, and always willing to listen to my research ideas. Thank you. And the POP group has been very supportive of my research, so supportive that I feel that there are no boundaries between our groups. Kirsten and Katie, especially, they have been very helpful during the later years of my PhD, and my best work would have been impossible without their support. And Connor and Victoria helped me get started during my initial years, and yeah, thank you for that. Thanks to my other friends from other groups too. Being an experimentalist is great because it taught me to rely on so many different people and their expertise, and also help others when they need it. I want to acknowledge the amazing support from the SNF staff, which made my experimental work a smooth sailing, especially Usha and Dr. Jim McVitie. Yeah, they were the lifeline of the etch process and the 2D device community, respectively. I also want to thank my other friends and colleagues from internships, industry collaborations. And finally, I want to acknowledge my friends and family. My friends at Stanford and outside Stanford, they provided me a very good support system, and also my relatives in the US. Thank you for that. Yeah, it really made this place feel like home. And finally, I would like to thank my parents and my brothers. I would not be here without your support and guidance. Thank you for being patient with my PhD progress. Thanks.
Well, the floor is open to questions. How do we do that, Rina? What do you prefer? Just extempore, or should they?
Yeah, just unmute. I think they can unmute themselves. Yeah.
Okay. Go ahead. Anybody has any questions? I don't see anything on the chat, so I guess no questions. Yes.
Somebody has to ask something, because we're holding all our questions for the closed session.
Right.
Yeah, you should have planted some questions for your friends.
Or that.
I'll ask a question. Hi, can I ask a question?
Yeah, hi, Kevin.
So,
yeah.
Hey, so you mentioned that thermals are sort of stopping the on current. Is that the death of a 2D transistor? And how do you fix it?
Yeah, so I would say the way to fix that would be to look at different dielectric interfaces and also different encapsulation. So there are only three ways to sink the heat from the channel, using the back dielectric interface, the top encapsulation or top gate interface, and the contacts. So yeah, I think more attention has to be paid for the thermal properties of the interface here.
Okay, thank you.
Yeah.
I think Christine has a question in the chat box.
Okay, let's see. I'm not
Knowing what you know now, if you were just starting a PhD in this field, what problems would you work on?
Well, that's a hard question. I think, yeah, I would still work on the contacts again. I mean, it's a very hard problem, but it's also very fulfilling when you make some progress on it. So yeah, I think when I started, this was the major problem holding back 2D semiconductors. So yeah, that's what I would have chosen. Yeah. Thanks, Kirsten.
I'll ask a question that it's probably better for the open session, and it's a little bit related to Kirsten's. What advice would you give your younger self? This is a question maybe that if you know, knowing what you know now, what advice would you give yourself from 5 years ago or whenever you started? This is more from the point of view of the junior grad students who are listening.
Yeah, I would say don't put all your eggs in one basket. Try out different ideas. And this is research, so it's almost like rolling your die. So if an idea doesn't work, don't be too faithful to it. Keep moving and keep iterating. Look at new ideas. Yeah. Because I spent 2 years on a project trying to integrate 3-5 heterostructure contacts on MOS2, and it didn't work. So yeah, I could have spent that on other ideas. Yeah.
By the way, do you know why that didn't work? What was what stopped it?
The problem there was the processing issues. The 3-5 growth itself is damaging the 2D material because it has to be done in a hydrogen ambient at high temperatures. So we really couldn't find a way to integrate it without destroying the mobility of the channel.
I see.
What about some advice to you, your younger self, for collaborative activities?
Yeah, I would say more collaboration is always better because it reduces the work and it has a multiplier effect. So I probably should have collaborated more in the early phases of my PhD. Yeah. But because that's also when you're not sure of what you're doing, and others' expertise would help. But I was kind of in the dark during that time, trying to do everything on my own. So definitely, I wouldn't recommend that.
Yeah, comment on your rolling a dice comment suggestion. I hope the choice of research project is better than rolling a dice, because you have done the literature search and you have done some background study. So you should have tilted the odds in your favor already and not just rolling a dice.
Yeah, I agree. That's true. Yeah.
There are a couple of questions in the chat section.
So how does mobility change with the channel length after ALOX capping? So the capping does improve the mobility, and we see that with the capping, the scale length increases. So the short channel effects are more into play at the with the ALOX capping. So I don't know if the question was about how mobility is different for different channels, but I would say that short channel effects are greater. So, you have more depletion in the channel, and that would reduce your channel resistance when you increase the capping or when you have the capping.
There's another question from Katie.
Yeah, if you were to go about choosing another set of metals for a different alloy contact, can you discuss your thought process for choosing that set of metals? Yeah, so the main considerations here are, first, the capping metal should be, first, let's say we are looking at N-type contacts. We want the damage-free or the damage reduction layer to be low work function. So it's going to be very easily oxidizable. So you want the capping layer to be kind of immune and protect the underlying layer from oxidation. And I would say platinum, palladium, nickel, these are good candidates because they are relatively stable, but they're also CMOS compatible. But if you want to, so for the underlying layer, I would say indium and tin are good choices. We can try bismuth. But if you want to go for P-type contacts, and there you need high work function, then you start running into toxic chemicals like tellurium and selenium, but they are really high work function. They have low melting points, so they are good candidates, provided we can kind of work with it in a safe environment. Oh, Raisel, okay.
Interesting
Raisel
comment. He says, 5 years ago, I defended on this same day, May 3rd, Best wishes. May the fourth be with you.
Can I ask something?
Yes,
Go ahead.
hi Kwan.
Yeah, nice to meet you. And I was very impressed with your research, and congratulations. Actually, I think your device is backgated TFT. In this case, I think source and drain might be electrically doped. So if you use top gate, then how the contact resistance change it? And the second question is, how do you think if it would be fine if you set contact resistance at source and drain it's the same, like and set as 2RC? Because in previous page, in your COMSOL simulation, the field seems like different at source and drain. So I'd like to ask about that.
Yeah, thanks for the question, Kwan Ho. For your first question, I would say for most contacts on this monolayer MOS2, the carrier injection happens mainly at this contact edge shown here. So even in a top gate case, if we could gate this vicinity very well, by having this gate overlap, I think we will get decent contact resistance. There have been some recent work in last year's IADM where they did top gated bismuth contacted transistors and they got good contact resistance. The back gate is still the best, but yeah, if you want to adopt this for logic and you want to go to top gates, yeah, having gate overlap. But if you don't want to overlap the gate, then yeah, we have to develop these extension doping schemes. So we can use all the recipes available, and the problem here is lifting it off and seeing if the doping still works. But there are also other techniques to dope this region, the TMD region, from the back. For example, phosphorus doped silicon glass, which is basically phosphorus atoms implanted in silicon oxide that can dope these regions. We can use aluminum oxide passivation layers which have negative fixed charge. So that would be great for PMOS transistors to induce holes here. So there are ways to do it, I would say. To your second question, yes, there is a asymmetry between the source and the drain. And generally, we expect the source resistance to be higher because the drain resistance has this large voltage across the Schottky barrier. So, but the RC that we estimate is the sum of the two. So, I mean, multiplying the two should give you the total parasitic resistance.
Yeah. Okay, thank you.
Yeah.
I guess Raisul has another question. I'll read it. For a backgated transistor, how thin could the oxide be before the source drain to gate leakage starts to become dominant?
Yeah, the limit I would say for the 750 Celsius MOS2 growth was 30 nanometer silicon oxide. The reason I'm mentioning that is that MOS2 growth is the main the problem. It damages the silicon oxide substrate. So any thinner than 30 nanometers, yeah, you start running into a lot of leakage. Okay, thanks, Raisul.
Okay, well, it's 2:30. Let's close this session and then we will put Aravindh under the guillotine. And I'm just joking.
Okay, thank you everyone for coming.